Hello. So last time we were speaking about a simple model describing, at least from a qualitative point of view, but not really qualitative because we also have a formula, the concept of impedance of an electrode. So I just want to go one slide back. So we said that the impedance of an electrode theoretically should be purely resistive and is inversely proportional to the radius of the tip of the electrode. So the sharper the electrode, the higher the impedance. Then in real life it's not really like this. I mean, this proportion is still maintained, but the electrode is not a pure resistance because our model is too simple. Then, for instance, when I said that this wire is insulated, I mean, this wire is very thin compared to the sphere in this drawing, but in real life it's not so thin because it's the shaft of an electrode, so the electrode is something like this. So even if this wire is insulated, so it's not in contact with the fluid, still it contributes to the electric field. So the electric field in this region will not be exactly the one of a sphere. Then the container here is not infinitely big and far. So there are a number of approximations that more or less allows us to compute all those integrals in a simple way, but in real life it's not like this. So what is this fluid and what is this container? So if we think of neurons in a brain inside the head of an animal, the head of an animal and the entire body of the animal is surrounded by the skin. So the skin contains some fluids, and this thing is conductive, so it's completely surrounding the brain. There are no apertures for the brain. So this kind of vessel, which here is a perfect conductor, in real life it would be the skin surrounding the brain, and the fluid which is here would be the fluid which is inside the brain. So this is just a simple model, but still it gives us an idea. Then why we need to know this kind of thing? For basically one reason. So if we go now to our blackboard, so let's think of this situation. Let's say we have a brain. Let's make it like this. Let's say an area like this. And then you have some neurons. I draw them as dots. So sometimes what we are interested in is to try to isolate the signal from one neuron, the signal of one neuron from the signals of the others. So all of them are emitting and receiving spikes. They are interconnected. The action potential is something that allows the information to go from one place to another one. It's a communication that occurs from one neuron to another one, but we can have part of this signal also outside of the neuron, because the electric field propagates also outside. Then it decays with the square of the distance, the Coulomb's law, for the, let's say, electrostatic field. And so if you put an electrode here, for instance, now in blue I draw the tip of the electrode. Let's say we are like this from above. So the farther you go from a neuron, the weaker the signal you will receive. When you do single neuron recordings, like in patch clamping, you basically know where the neuron is. But if you do, for instance, extracellular recording in a tissue of brain, then it's difficult to locate the neuron. So basically you put an electrode in a region, and then the place where you go is random. I mean, you know you are in that region and not in that one or in that one, but exactly centering the neuron is basically impossible. Sometimes it happens, and you see this on the trace on the oscilloscope of related to the action potential, because the polarity of the action potential is inverted because you are inside the membrane. But it's rare. Let's say most of the time you are out of the membrane. So here, ideally, what you would like to have is an electrode that can feel only the signals from one neuron if you are interested in a single neuron recording. So you would like to have an electrode that feels something, let's say, around a sort of sphere of interaction. So imagine the tip of the electrode and the sort of sphere of interaction out of which the signals are so weak that the electrode is not able to capture it. So this sphere of interaction goes with the impedance of the electrode. So the lower the impedance of the electrode, the higher the sphere of interaction. And so if you have another electrode like this, now I draw it in a different color, you put it here with and let's suppose that this electrode will have a bigger sphere of interaction. So this green electrode is able to capture signals from all the other neurons in this region. Then all those electric fields will be summated here, but we know that those electric fields correspond also to currents. So there will be electric currents reaching this electrode here, let's say from all the other neurons like this, and they will be summated because they are converging to the same node, the algebraic sum of the currents, so the Kirchhoff's law. And so this electrode will have a signal, which is the one that we later amplify with the instrumentation amplifier, which is a sort of average of all the signals produced by those neurons, which is a sort of pedestal, which is called the local field potential. While this other electrode, having a small sphere of interaction like this, will be not able to listen to all these other neurons, but only to this one, maybe, if it's close to it enough, or maybe to 2 neurons, but not all of them. So in this situation, this green electrode is the one that we call the reference electrode, and the blue one is what we call the electrode, or let's say the signal electrode. And we still need a third electrode, which is the ground electrode. So this is ground electrode. Why? Because it is true that the differential amplifier is taking the difference between the signal and the reference, but they are both voltages, so they have to be a common reference to a 0 point that we call ground. So in fact, one voltage is the voltage difference between the reference and ground. The other voltage is the one between signal and ground, and the differential amplifier takes the difference of those two differences. So this ground electrode is important. We cannot disconnect it. And also you can't connect the reference directly to the ground. You will see something, but it's as like as the population of neurons you are listening to is the entire brain. Maybe you want to do so, but at least you have to be aware of this. And then, secondary, if you connect the reference directly to ground, then you don't have the case that those two electrodes, now the green one and the signal one, the blue one, are close each other, so they are not picking up, let's say, almost the same noise. And if they don't do this, then when the differential amplifier will take the subtraction, you will not a noise cancellation. So these are key points, fundamental points for the recordings in electrophysiology. Sometimes people have the tendency of connecting the reference to ground because they see noisy signals, and then they say, okay, if I connect this to a good ground point, then I don't see the noise. That might be true, but you have to be aware that maybe by doing so you are not recording what you are supposed to record, because of course if you put everything to ground, also the signal, you short circuit to ground, then you have zero. And then you say, okay, there is no noise. Yes, true, but there is also no signal. And so you have to be careful about this. Most of the time, this trick is done because the reference electrode is not good. Maybe it doesn't have the good impedance. Imagine, for instance, another situation like this one. Like I have a population of neurons. One neuron here, one here, one here, one here, one here, like this. So they are sparse in an area. Then you take one signal electrode with this sphere of interaction, and then you put a reference electrode in another place, but you take the reference having the same geometry of the signal electrode, so something like this with an interaction sphere like this, and then you call this reference and you call this signal, and then you have the ground here. So you say, okay, everything is good. Those two electrodes have the same sharpness, the same radius, but the blue one is listening to the action potential of this neuron. The green one is listening not to an average, that on average is, let's say, kind of constant, but to a signal like this, and then the differential amplifier is just taking the signal, the difference of the spike trains recorded here respect to this one, which is something that makes no sense, because this is not what you want to do. So you're recording a difference between two signals that maybe are not even correlated each other, so or maybe they are correlated, but who knows, they can be anything, so it makes no sense. It's like if I want to measure the distance, the length of an object, and instead of measuring the length of an object, from this point to this point, I say, okay, this point is wherever, and this other point is in another place, and then I put a ruler and I take the difference. Okay, you have a difference, but what is that? That is nothing. So it's let's say a random number. So we have to be careful about these key concepts, because these are the main source of problems in those types of recordings. So now I go back to the presentation. Okay. So this is basically what we said, the impedance of an electrode, this kind of thing. Then this one was important. The resistance of an electrode is not the resistance of the wire it is made of. It is this resistance that appears because of the resistivity of the fluid. Okay, we also said something like this, that there are some approximation. And another interesting thing is that if the ground electrode is large, let's say, then the impedance of the electrode does not depend on the place where you put it. So let's say, in other words, if you are swimming in the bath of your home, then is one thing, but if you are swimming in the ocean, basically you are far from every coast, wherever you are. So now there is another important thing that goes with these concepts. It's the concept of noise of a resistor, which is also connected to the sensitivity of an electrode. So this sensitivity sphere, this region where an electrode is sensitive. So we know that we can have a resistor like this, and we know that a circuit like this, so without any battery, will make no current flowing in this resistor. So we have to take a battery and attach it to it like this. So this battery will have a voltage, the resistor will have a resistance, and therefore there will be a current flowing in this circuit. But this is not completely true. Let's say it is true from a theoretical point of view, but in practice, if you have a resistor like this, and this resistor is not connected to anything, but it is placed in a room, in a place, in an environment having a certain temperature T, then there will be a current flowing in this resistor, let's say up and down like this. And therefore there will be also a voltage, because of the Ohm's law, a sort of alternating voltage, in a way that the average value of the voltage you can measure from this point to this one is 0, but it's not 0 because the voltage is flat, but because there are symmetric fluctuations like this. So why it's like this? Well, because the temperature will make the electrons inside the resistor to shake. So the temperature is interpreted as energy of those particles, the electrons. The electrons, we know they can move in a conductor, so if they receive energy they will move. They will move in random direction like this, so they will not have a drift like this, so they don't move like this if they don't have an external field that are pushing them towards a preferred direction. They just move around the place where they are, but they move. So if they move, they create a current. If they create a current, they also have a voltage. So if you take if you take the Boltzmann distribution for this energy of the electrons, then it is possible to compute what is called the Johnson-Nyquist noise, and more specifically the amplitude of that noise for a given temperature T, given the resistor of the electrode, and also given a delta F, which is a bandwidth of interest for this type of noisy signals that you can have. So this delta F is set by the sampling. So we record this signal within a certain bandwidth. We can set by the sampling frequency and also the anti-aliasing filter. And then if we record this signal that is moving up and down with zero average, let's say the peak of that signal is according to this. We delete something, otherwise we don't see anything. Okay. So why is that important? Because if we plug all the numbers here, for instance, okay, for the Boltzmann constant, 300 is the room temperature in Kelvin. It corresponds to more or less 25 Celsius. If we put a resistor R equal to 1 mega ohm, so 10 to the 6 ohms, which is a popular value for the impedance of a very sharp electrode used in electrophysiology, and we put 20 kilohertz as a sampling rate, then we have that this value is 18 microvolts. So this is a standard value of noise that you can have at the tip of an electrode when you put it in close to a neuron, and this is the level of noise. So it means that whatever is below that level will fall into a sort of background of noise, and then it's very difficult to see if you have a signal which is very weak like this. So basically, let's say, to simplify, a signal that is weaker than the thermal noise in an electron is lost. And you can choose what is the Johnson-Nyquist noise level if you tune the resistor of the electrode. So you see that the lower the resistance of the electrode, the lower the noise. It means that if you have an electrode with a very low resistance, in principle it has a very low noise, and therefore it can capture weak signals. So this is how you tune this range of sensitivity of an electrode, by tuning the impedance of it according to the Johnson-Nyquist noise, which is there because of thermal instabilities of the electrons.